Welcome all of you. Last week we were discussing about Fourier transformation, Fourier series I introduced. As you know, Fourier transformation is one of the basic requirement in NMR spectroscopy. It is one of the important mathematical tool that we use. As we have been discussing right from the beginning, we apply radio frequency pulse, collect the free indentation decay as a function of time. The time and frequency are related to each other by a mathematical operation called Fourier transformation. So, it is good to know something about Fourier transformation, what is Fourier series, how Fourier what is the difference between Fourier series and the Fourier transformation, and how we can utilize Fourier transformation in some important applications in NMR spectroscopy. So, in the last class I started introducing the Fourier series and then discussed about for a periodic function we can express this periodic function as a series called Fourier series, where we have summation a0 plus summation as a function of an into cosine of x plus bn into sine of x, all those things we wrote. And then we also understood how to calculate these Fourier coefficients, that we did, and we took an example of a periodic function which is a square wave and tried to arrive at what are the Fourier coefficients for this thing. And in fact, what we did last time, see, we evaluated for this square wave we took, and this is what we defined the function f of x, which is equal to 0 in this region and it is 1 in this region. And of course, I calculated a0. a0 is simply the integral of this function, and we showed it, I do not want to go it again, to be equal to 1. So, a0 is 1 for this function, and then for n not equal to 0 we have to evaluate this integral, and again separating into two parts, minus 5 to 0 and 0 to 5, we know how the function is behaving and different regions, and of course this will go to 0, and we also worked out this turns out to be 1, and we calculated what is an. For n not equal to 0 we showed that an equal to 0. I do not want to go through the steps again because it was discussed last time. Similarly, we also evaluated bn. Bn again integral of the sine function, and then again what will happen, we resolve into minus 5 to 0 of this for this function, that part will go to 0 and the other integral survives, 0 to pi sin n x dx will survive, and then substitute the limits, and finally what we are going to get is this one. This I said the value of bn is 0 for even n and it is 2 by n pi for odd values of n. This is what we worked out last time. But now we substituted this coefficient in the basic equation or expression for the Fourier series. In that we know what is already a0, a0 is 1. So, we got it, and for this is equal to 0 for n not equal to 0. So, that means for any value other than n not equal to 0, that means a0 survive, a1 to any other values it will become 0, though this term will not survive, it will go to 0, and we have to deal with only bn sin of nx. And again an, if you want to see this bn, for even values of n we also showed bn is 0. So, if you substitute all these Fourier coefficients what we calculated, the final form of the series is like this, because a0 is equal to 1 and a0 by 2 is half, and then this is 0, and the sine part, even part will 0, only odd part will survive, odd part we are writing like this. This is the Fourier series for the square wave which we considered. Of course, what happens if I shift the let us say x in the function by pi by 2 in the previous problem. Now, you write this thing, earlier it was here, I took this as 0 and I knew this was 0 and this was 1, but now I shifted by pi by 2. So, I call this function h of x, which is equal to f of x plus pi by 2, shifted by pi by 2. So, that means you can define the values for this. H of x equal to, for this function is equal to 0 for minus pi less than equal less than x less than minus pi by 2 in this region, and of course it is equal to 1 for minus pi by 2 to plus pi by 2, and equal to 0 again for plus pi by 2 to pi. So, these values can be defined for this function. All we have to do is in the previous equation, previous problem we solved, we worked out the Fourier coefficients final form. Simply replace x by pi by x plus pi by 2. That is all you have to do in the previous solution. not in the above solution, in the previous solution. So if you do that, then what you have to do, plus remember the trigonometrical operation, sin of x plus y by 2 equal to cosine of x. So whatever you wrote there previous, it written like this. Instead of the sine series, you are going to write it as a cosine series here. You see here, it was a sine series here, but we are going to write as a cosine series. That is what going to write here. Okay. So this is an example for this. Next, I will go into another form of Fourier series called complex form of the Fourier series. You should know what is a complex form of the Fourier series also, because Fourier transformation is a, when we do the Fourier transformation, we get both real and imaginary part, like the complex number. So we should know something about the complex form of the Fourier series before getting into Fourier transformation. So what we are trying to do is, of course you know the basic equation. What if we have a sin of n of sin n of x, it can be written as exponential e to the power of I n x minus of e to the power of I n x over 2i. This is a well known trigonometrical formula. Similarly, cos of n x also is well known. It is e to the power of I n x plus e to the power of minus I n x by 2. These two sin n x and cos n x is a well known formula. It is available in all basic trigonometry books. Now what we do is we have to substitute for sin n x in the and cos n x in the general expression what we wrote for the Fourier series. We wrote Fourier series, remember, f x equal to f of a of 0 plus of summation over cosine of n x and sin of m x. All those things a and b and everything we wrote. For that basic Fourier series expression, we have to substitute this thing. So if you substitute this, f x turns out to be a0 by 2, and then of course do a simple mathematical jugglery after substitution. Then it turns out to be an minus ibn by 2, because we are talking about sin and cosine expressed in terms of e to the power of I n x plus e to the power of minus I n x by 2 and other things like this. And then this is another part you are going to write. This is for the cosine part, this is for the sine part. Okay. Now what I am going to do is, for solving this equation, I am going to let C0 as a naught by 2, and just I am defining, and then Cn I am going to define as an minus ibn by 2. To ease of my operation, ease of my calculation, I am defining like this. Similarly, C of minus n I am going to define as an plus ibn by 2. Okay. So now substitute this in this basic expression for the Fourier series. If you do that, then it turns out to be minus infinity plus infinity Cn e to the power of I n x, it turns out. It is a very simple mathematical jugglery you can do by substituting these terms. Then what you are going to get is, you are going to get C0 plus C1 e to the power of ix and C minus 1 e to the power of minus ix, like alternately n equal to plus 1 minus n equal to, it can be 1 and plus 1 and minus 1, plus 2 and minus 2. So you can write down C1, C2, C minus 1, C minus 2, etc. expressed in terms of exponential form like this. This is simple jugglery of the mathematics. I have not done anything new. It is all well known simple arithmetic. Then it turns out to be summation of minus infinity plus infinity Cn of e to the power of I n x. This is what is finally we are going to get for fx. Okay. Now the question is, we know this is fx, but we need to work out Cn. That means we have to work out C0, Cn and Cn minus C minus n also. All these three coefficients we need to work out. How do we go ahead and do it? For getting C0, all we have to do is we have to integrate this function of fx on both sides. We have written the fx now, complex form of it. What I have to do is take the 1 over 2 pi, integral from minus pi to plus pi, fx dx I will integrate. Then this turns out to be C0 into 1 over 2 pi minus pi into plus into integral of minus pi to plus pi dx, plus all other terms will come into picture. This is from the previous expression, it is written here, we have already worked out, you see, from this. So now this is what I did. Remaining terms, what happened to them? You can work out and see all the terms are 0. All other x, only this term will survive. Okay. This is called C0. So that means C0 survives, all other term goes to 0 when I integrate this function fx on both sides from minus pi to plus pi. But that is integral limits. So C0 I can write as C0 equal to 1 over 2 pi integral of fx dx. This is the expression for C0. So if I know our fx, if I integrate that function over minus pi to plus pi, I can calculate C0. I can find out coefficient C0. For how do you get Cn now? For getting Cn, what we have to do is, instead of just integrating the function on both sides from minus pi to plus pi, multiply by e to the power of minus in x and integrate on both sides. That is what we have to do to get C of n. So, if you do that, simply I am multiplying the function by e to the power of minus in x and dx, and then if you do that, of course, we can resolve this into different terms like this: 1 over 2 pi minus pi to plus pi C0 Cn. Cn, of course, n takes from all the values minus n to plus n, etc. But here we are considering plus of n, Cn. Okay. So, now we know the basic operation e to the exponential function e to the power of in x into e to the power of minus in x equal to 1. That is well known. Of course, that you use this here, it turns out to be e to the power in x plus e to the power of minus in x you come across, that will become 1. So, using this operation, you will show that this turns out to be equal to 1 over 2 pi into minus pi integral of minus pi to plus pi Cn dx. All other terms are again 0. It turns out to be 0. So, it is a simple basic elementary integral calculus I did and showed that Cn is equal to this function is equal to Cn into 1 over 2 pi into minus pi to integral of minus pi to plus pi dx. So, this is our Cn. So, now what I have to do is to calculate I substituted Cn, I got the Cn. So, essentially I write Cn as like C0 I wrote, which is the integral of minus pi to plus pi f of x dx I wrote over 1 over 2 pi came. Similarly, now integral of Cn if I have to obtain 1 over 2 pi into integral of minus pi to plus pi f x dx in x, if I integrate I will get Cn. This is what I wanted to show you. Now, I need to get C minus n also. Remember, that is also I also have to obtain the coefficients for minus n values. In this case, you have to do slightly different. Previously, we multiplied that function by e to the power of minus in x to get the Cn. Now, to get C minus n, multiply by e to the power of in x plus in x and integrate. Simple jugglery we are doing, nothing else. So, substitute e to the power of in x to obtain C minus n like we did here. So, Cn if you want to get, I do this. C minus n if I want to do, I will do this one. I know I told you already what to do if I want to get C0. So, all the 3 types C0, Cn and C minus n, all the coefficients we can obtain by simply integrating the function from minus pi to plus pi, this fx dx. In one case there is no multiplication for C0, but in other case you have to multiply by corresponding exponential function either minus in x or e to the power of plus in x, and then integrate and do this substitution. So, this is very easy. So, this is what we have to do to obtain the coefficients C0, Cn and C minus n. Okay, this is the way to express the complex form of Fourier series. Now, we will do one thing. We can solve the square wave problem which we solved using the Fourier series in a conventional way. Now, can we solve the same problem using complex form of the Fourier series? That means, instead of A0, An, Bn, we need to work out C0, Cn, Cn minus. And I already told you, we have discussed how to work out these coefficients. Let us do this exercise. Of course, earlier we have already defined this function square wave, and this is the value for fx equal to 0, for minus pi to 0, and then it is equal to 1 in this range. This function values are already in different ranges are known, value of this, how this function behaves in different ranges. Okay. Now, C0 as I told you, integral 1 over 2 pi, just integrate the function from minus pi to 2 pi fx dx without multiplication by exponential. That is what I told you. So, do that one. Okay. Now, again this function we can resolve into 2 terms, minus pi to 0 and integral fx dx plus 1 over 2 pi integral 0 to 2 pi fx dx. Same minus pi to pi integration I have divided it into 2 steps, 2 parts, minus pi to 0 and 0 to 2 pi 2 integrals, that is all. Of course, this part is already know fx equal to 0 in this range. So, now we have to deal with only this one, here fx equal to 1. So, what does it mean? This turns out to be 1 over 2 pi into integral of 0 to pi dx. This is nothing but x. Okay. So, it is nothing but 1 over 2 pi. If you substitute the limit, it turns out to be pi. So, you cancel this pi, what you are going to get is half. So, that means for this function, for C0 we got half. Very easily we worked out using the complex form for this one. So, C0 we know. What are the other things we have to do? We have to work out now C of n and C of minus n. So, C of n I already told you, take it from minus pi to plus pi e to the power of minus I n x. Again we know in this range integral from minus pi to 0 for this function f x equal to 0. You do not have to consider that. Consider only from 0 to pi f x e to the power of minus I n x dx. And this one, if you write like that, of course this value is 1 in this region. So, it turns out to be just 1 into this one. I did not write 1, but it is all simple integral calculations. Integral calculus, I guess you all know this. So, this turns out to be 1 over 2 pi into integral of 0 to pi 1 into e to the power of minus I n x dx, which is nothing but 1 over 2 pi into minus 1 over n I into e to the power of minus I n x. This is what I did, integration of this function. Now, this limit is from 0 to pi, substitute this limit. Minus n I, you know that if this comes in the denominator, minus 1 over n I into e to the power of minus I n x dx. This is the simple integral form for this exponential function. So, substitute the limits. When I substitute the limit for n, which is equal to 0 to pi, you see that this turns out to be 1 over 2 pi n I into e to the power of minus I n pi into e to the power of 0, minus e to the power of 0. This is 1 again. So, when you do that, this part we did some jugglery. This we can resolve into sine and cosine components. We know that trigonometry e to the power of I x we can express as sum of sines and cosines. So, this we resolved expressed as cos of n pi into plus I sin minus n pi. This is the e to the power of minus I n pi. This basic trigonometry you should know that cos n pi. So, this in plus I sin minus n pi, this is the way we have to write. Simple exponential form expanded as cosines and sines. Of course, minus 1 we already got it. So, now what will happen if you look at this function? For n is equal to odd number, the terms in the flower bracket here goes to 0. I am sorry, goes to minus 1. For n is equal to, for odd, all the if you calculate this term for putting n equal to 1, 3 and 5 is simple trigonometrical function. You put n is equal to 1, 3 and 5 all odd terms, then you find out the bracket turns out to be minus 1. So, what will happen? And then for n is equal to even if you consider, it is going to be plus 1. Okay. Now, when it is plus 1 and minus 1, what is going to happen? You look at it. For Cn, we can simply write as 1 over n plus n into I, n into pi into I. For n is equal to odd, Cn is equal to 0 from this equation. Okay. I am sorry, this is 1 over n pi I for n is equal to odd, and it is 0 for n equal to even. Right. So, from this you can find out when n is equal to even, it is plus 1. Plus 1 minus 1 here cancel, this term becomes 0. That is what happens. So, for n is equal to even number, Cn is equal to 0. For n is equal to odd number, Cn turns out to be 1 over I into n into pi. These terms we know. So, we have worked out Cn and we know C0 and simply substitute for this fx and express this one. This is when you substitute for this function in exponential form. We already wrote the exponential form of the Fourier series. Simply substitute these coefficients and write down C0 we got as 1 by 2, and for the odd values of n we got this one, and simply for n equal to plus n and minus n substitute this. For n equal to plus n it is positive sign, for n is equal to minus n minus 1 2 3 it is going to be minus 2 minus 1 minus 2 minus 5. So, this all turns out to be negative. That is all is going to happen. So, now you can simplify it in a simple way. When you have exponential function like e to the power of ix and e to the power of minus ix, you can combine them like this. Okay, e to the power of ix minus e to the power of minus ix by 1. Similarly, this term like this. Very simply you can combine all these terms like this, because I have plus n and minus n, both the values are there. As you can see here, we have for plus n e to the power of I5x, for minus n e to the power of minus 5x. Similarly, for all odd terms you have plus and minus, combine them like this and then make a simple jugglery. If you combine them, this turns out to be, remember in the very first time I showed you how do you express sine term, sine and cosine in terms of exponential function. This is nothing but sin x, sin 3x by 3, sin 5x by 5, etc. It is a series like this. So, the fx, if you when you express for the square wave in the form of the complex number, complex series, it can be written like this. So, this is a simple complex form of the square wave in the expression of the solving the square wave using the complex form of the Fourier series. Then a function fx turns out to be this one. So, you people should simply know what we have been doing is we are solving this using a simple trigonometry. Okay, integrating the function from minus pi to plus pi. In one case we do not multiply, in other case we multiply by e to the power of minus I pi n, in other case we multiply by e to the power of plus I pi x. Like that, very easily you substitute this thing and make a simple integral calculus. Afterwards, when you do the integration, all you have to do is to combine the terms based on the terms like e to the power of phi x plus e to the power of minus I x, all those things. Then you can express in terms of sines and cosines. In this case, for even number, cosine part was 0, so we got only cosine part. So, this is all I wanted to tell you something about Fourier series. This is the Fourier series we were trying to do only for the periodic functions we can express as Fourier series. Supposing the function is not periodic, what can we do? So, we will discuss something about what a new term, a new mathematical operation called Fourier transformation. This is something which I am going to discuss now. This is, of course, if a function is non-periodic also, we can express this, the Fourier series, somehow we can do the mathematical operation and get a continuous function, and this is a Fourier, this we call it as a Fourier transformation, a mathematical operation which I am going to discuss now. See the Fourier transformation, what we are going to do. Again consider a simple rectangular function. This is a rectangular function. Please note, it is not periodic. It is just a pulse I have written, rectangular function. It is from minus half to plus half is the limit, and this 0 to 1. This is the function I have written. So, this function can be written as f of t equal to 1 for modulus of t less than half, equal to 0 for modulus of t greater than half. This is a simple thing what we have written for the function. This is a square function I have written. Nothing new. It is not periodic as you can see. It is a single standing pulse. Now, it is an even function centered at the origin. Remember, it is an even function like a cosine function. All even functions will be symmetric with respect to the y axis. Okay. Now, it is not periodic and hence does not have a Fourier series. But if I have to solve it, what do I do? So, what I am going to do is, we can make it periodic artificially. What I do is, just for calculation purpose, for understanding Fourier transformation, I am going to do some simple jugglery. What I am going to do is, I will periodicize this type of function by repeating it at regular intervals. What I mean is, I take this function, repeat it after some time here, this side, this side, this side. You can keep on repeating, considering this as the base function. It is possible to do that. Like, for example, I am periodicizing the function at regular frequency intervals of 2 and 4. For example, here this is a base function, and this is periodicized at period 2, it is repeated, at period 4 it is repeated, similarly minus 2 and minus 4 it is repeated. It is not periodic, I deliberately made it periodic, I periodicized just to make my mathematical operation simple or to understand some concept. Same thing if I want to do periodicity 4, it is like this. Instead of 1, 2, I have written it minus first flow minus 4, then again 8 and minus 8, it goes like that. So, this intentionally, artificially I have made it, I have periodicized this function at different integrals, I mean at different frequencies. Let us do one thing. Let us take 3 such rectangular functions which I have periodicized at regular intervals, like the periods could be 2, 4 and 16. Why? I took this number, any number is fine. I have already shown you for 2 and 4, some another number, big number. In fact, I wanted to go to 32 or 64 to show as the interval becomes bigger and bigger, the frequency becomes closer and closer, and then it becomes goes more towards the continuous function. That is why I want to take a bigger number, but anyway 2, 4 and 16 I have chosen. Okay. These are the periods I have chosen I deliberately periodized this type of functions at 3 intervals. Now, what I will do is, I will calculate the Fourier coefficients for this. You know how to calculate the Fourier coefficients? Already we worked out a n, b n, c and all those things. In the complex form c0, cn minus 1, we know how to calculate. It is a simple integral calculation. We did that, integral calculus. So, we can do that. artificially periodized for period 2, 4 and 6, calculate the Fourier coefficients and then plot it. Now plot the Fourier coefficients like this for period t for different values of n equal to 0, plus 1, 2, 3, 4 minus, you calculate the value and then start entering here and then plot like the stick plot. For period 4 is like this. For period 16 it is like this. Already you can feel it what is going on as the period keeps on increasing. Here when the period was only 2, the frequencies were well separated, they were dispersed more and more. As you increase the period, 2 became 4, it became closer and closer. So you go to 16, it became even closer. Now I take a large number instead of 16, 64 or 32, 64 or 128, what will happen? This type of period function become more or less continuous. You can treat it as a continuous function. So that's what happens. So we know the general form of the Fourier series, that, and then what we are going to do is we will see in this case we put t is a period. I already explained to you, and it is in the denominator. The frequency is 1 over t, that you know. Period. If you know the period, I can calculate the frequency, which is 1 over t. So now for the frequencies are 0, 1 over t, 1 over 2t, 1 over 4t, it keeps going. You can calculate for this capital T. As t increases, what is happening? We saw in the previous graph I showed you. As t keeps becoming bigger and bigger, larger and larger, the frequencies became closer and closer. As I will show you, you can see here frequency became very close, here well separated, here more dispersed. So that is the advantage. So when t becomes larger and larger, the frequency becomes closer and closer. Okay, that is a concept you understood. Now what we can do is we can calculate this function t, f of t, Fourier coefficients for this. This is the Fourier series. Let us calculate the Fourier coefficients. But remember, I started this as a non-periodic function. I only periodized just to understand what it is and wrote in this form. And now I want to calculate the Fourier series. Once I make it periodic, there exists a Fourier series for that. So and once there is a Fourier series, I can calculate the Fourier coefficients. That's what we will do. So I calculate Cn when I express in the form of exponential form, a complex form of the Fourier series. So we can take this from minus t by 2 to plus t by 2 and integrate this. Of course the function was known already, and for this is the general expression for the different t periods we have chosen. Now for the rectangular function what is chosen, the values are going from minus half to plus half. So accordingly we change the limits of the integration, minus half to plus half, and this is the function. And f of t in this region is 1. So integration boils down to simple term 1 over t, integral of minus half to plus half, e to the power of minus 2 pi n t over t. This is what I have taken, I have put it here. So now express this as 1 over t. Of course when you integrate this one, this term comes in the denominator and the limit is known actually, integration limits minus half and plus half, substitute it, then this turns out to be this one. When you substitute this one, then what will happen? Again further simplify it, little bit do the simple mathematical operation. I have not done anything more here. So this minus sign I removed it by bringing here, this bringing here, that's all I did, nothing else. Okay. Now this can be written as sin pi n by t, that is very well known. This can be written as sin pi n by t into 2 to the power of 2i. This is a trigonometrical simple operation which we discussed already. Otherwise sin n, if you write sin nx, I told you e to the power of minus it plus e to the power of plus it over 2i comes by bottom. So that one, if you want to express this, then this can be written as sin pi n by t into 2i. Okay. So in simple form it turns out to be 1 over pi n sin of pi n over t. This is a simple expression. If you work out this integral and when you write down the coefficients of this Fourier series, this turns out to be like this. Okay. Now when t is large, here go back here, when t becomes larger and larger, n by t becomes very very small here, because it is in the t is in the denominator. Now when this becomes very very small, in trigonometry we know that, let us say sin theta is there. If you have sin theta, when theta is equal to very very small, then sin theta can be simply written as equal to theta. That is a, you know, in trigonometry, basic trigonometry. So now for each when this tends towards 0 as a function of t, as a function of t, as t keeps on increasing, this tends towards 0. So this is what tends more towards 0. And this function, what I am going to do, which I got it here, I will scale it up. I multiply by t, does not matter, simply scale it up just for the sake of understanding. So this is why scaled up function. All I did is for the previous Fourier series which I have obtained, I multiply this by t, that is all. And this I can write like this, sin pi n by t over pi n by t. What I did is I brought it to the denominator. Why? Because I know this there is a special name for this function. You must be knowing in your elementary trigonometry, this is called sinc function, sin c by c function. So that is why I wanted to do that mathematical jugglery. So when t is very large, the frequencies are closely spaced, then we can replace the closely spaced discrete frequencies by a continuous function. That is what I wanted to tell you. See, now we took as a single square function, it is not periodic. Just to understand, we periodize at different intervals 2, 4 and 16. We understood as the t increases, as the period increases, what will happen? This becomes, frequency becomes closer and closer. So what I understood finally, it turns out to be a sinc function, and when t is very large, as I told you, n over t becomes close to 0, sin theta can be written as just sin theta, and when t is very small. Then we wrote sin of ns by s, whatever that function we wrote here, sin of pi n by t or pi n by t, and that is called a sinc function. You understand from that, when t is very large, the frequencies are very closely spaced. That means we can replace this discrete frequency by a continuous function. You understood? I started with a function which is only just a square wave. It was not a Fourier series, it was not periodic, there was no Fourier series. Just to understand how we can do artificially periodized and then obtain this thing. And then we can write the above equation as a simple term sin pi s over pi s. In the integral formula, we can write it as t into c of n. What is t? Cn is already obtained like this. I multiply just by this t, and then as t tends towards 0, the discrete values of n by t can be replaced by a continuous function. So what I am trying to say is, now there is a discrete value, it is changing only from minus t by 2 to plus t by 2. That is the integral values we have to take, limits of the integral from minus t by 2 to plus t by 2. But now as t tends towards infinity, tending towards infinity, the discrete values of n by t I can replace by a continuous function. I call it as s, some function f of s or so. Then the integral also changes because it is a continuous function. Instead of minus t by 2, I can go from minus infinity to plus infinity also. So accordingly I will change it. I will call this function as a continuous function s. Instead of f of t, I call it as f of s, because it is continuous. I call it as some other function, and now change the integral from minus infinity to plus infinity. The same thing remains. Now we can evaluate this integral for a rectangular function very easily. We know that rectangular function, again minus infinity to plus infinity, if you take this, we already worked out, minus half to plus half for the rectangular function what you have chosen, and this turns out to be sin pi s over pi s. This is called a sinc function. Okay, this is also called a sin x by x function. So for a rectangular function, which we took it until we knew the function from minus half to plus half, we worked out and then periodized and then calculated the Fourier coefficients by artificially periodizing, and then afterwards simple mathematical jugglery we understood, as the period keeps on increasing, the discrete function we can replace by a continuous function. So the limit of integral also can be changed from minus infinity to plus infinity. This is a general form for a function which is continuous. But in the special example of the rectangular function which was taken, it is from minus half to plus half. So then it turns out to be sin pi s by s, or in a simple form it is called sin x by x function, it is called a sinc function. Okay. And as the limit tends of this function, as x tends to 0, will become 1. This is what the rectangular function we saw. It is 1 from minus half to plus half we took. Okay. So, we can now formally define what is called a Fourier transformation. The Fourier transformation is given by a function like this, f of s equal to minus infinity to plus infinity e to the power of minus I pi minus 2 pi I s t into f of t dt. So, it is a discrete function. We keep on integrating over the entire range from minus infinity to plus infinity. It becomes a continuous function. So, discrete function can be expressed as a continuous function by doing Fourier transformation. The spectrum of a periodic function is a discrete set of frequencies. On the other hand, the Fourier transformation of a non-periodic function produces a continuous frequencies. You understood? So, this means this is the Fourier transformation of signal in real time gives you its frequency components. This is the conclusion which I wanted to tell you. Since the time is running out, what I am going to do is I will stop here. Today what we try to do is we continued from yesterday and understood what is Fourier series and expressed the complex form of the Fourier series, understood what are C0, C1 and C minus and how to calculate them by simple integration for C0 of the function f(x) from minus 5 to plus 5. For C of n and C of minus n, you have to multiply by e to the power of minus I n x, otherwise e to the power of I pi x and e to the power of plus I pi x. That simple thing we did, and then we worked out coefficients C of n and C of minus n, and then work out the Fourier series and solve that for a square function. And now what happened is we took a simple square function which is not periodic and then periodized for different values and worked out the Fourier series and plotted and found out as period increases it becomes continuous. So, what we try to understand is formally we can define the Fourier transformation of this discrete function, and the spectrum of this periodic function is discrete set of frequencies. But if I take the Fourier transformation of non-periodic function, it produces a continuous frequency. So, what we are trying to say, the Fourier transformation of a signal in time gives you the frequency components present in that. This is exactly what I wanted to tell you. So, this is what you come across in NMR. You collect the signal in time domain, do the Fourier transformation, you are going to get frequency domain. So, I will stop it here, we will come back and continue later with this point. Thank you.